So for our first two, convert to improper fractions. Right now they are mixed numbers. We want to get them into the form basically that we have over here, the improper fractions. So the 2 3/5, that 2 represents whole objects. The denominator, the 5, tells us how many pieces are in each of them. So to break them up into an improper fraction, we're taking everything and breaking it into pieces. So the 2 is multiplied by the 5 to make 10. Then we add that 10 to the 3 to get 13/5. The same with the 7 1/4. 7 times 4 is 28, plus the 1 is 29/4. Notice when we're converting improper to improper fractions, or the other way from improper to mixed numbers, the denominator of the fraction does not change. Okay, over here, going from our improper fractions to mixed numbers, we are dividing out with and taking a remainder. How many times does 3 go into 11? 3 times, with how many left over? 2, so it'd be 2/3. 17/4. How many times does 4 go into 17? 4, with how many left over? 1. So 4 1/4. Any questions on those first 4 problems? Okay, so we're good converting from mixed to improper and back again. So let's look at reducing. When we're asked to reduce, what we're basically doing is we're being asked to divide by common divisors, divide both numbers by the same number. So we have 28 over 42. Now we looked at divisibility rules last week, and I kind of give you a progression that I go through. Usually the first thing I look for is 10. Can 28 and 42 both be divided by 10? No. Remember, you tell by looking to see if they end in 0. They do not. Neither one of them, in fact, can be divided by 10. The next thing I usually check for is 5. Can either of those be divided by 5? No. They would have to end in a 0 or 5, and neither one of them do. How about 2? Can either of them be divided by 2? Yes, both of them can. If the last digit is even, it can be divided by 2. Well, both of those end in even digits, so they can both be divided by 2. So let's do that. 28 divided by 2 is 14. 42 divided by 2, 21. Can they be divided by 2 again? Well, the 14 can, but the 21 cannot. It ends in a 1. That's an odd digit. So then the next thing we would check is 3. Can both of them be divided by 3? No. The 21 can, but the 14 cannot. Remember, you can check that quickly by adding the digits together. 1 plus 4 is 5. 5 is not divisible by 3, so 14 is not divisible by 3. So then from there, we've got to look at those other prime numbers. 7, 11, 13, 17. Hopefully we don't go that high. But are there any of those that these can divide by? 7, good. 14 divided by 7 is 2, and 21 divided by 7 is 3. That's 2/3. So coming over to the 25 over 40, what can both of those be divided by? Any number that both of those can be divided by. 2 works. That's going to give me what? 12 over 20. Perfect. What's the number that they can still be divided by? 4 would work. 2 would have worked again as well. 12 divided by 4 is 3. 20 divided by 4 is 5. If we divided by 2, we'd get 6 over 10, and we'd have to divide by 2 again. So any questions on those two, reducing? Okay. Next, we have the 2/3. We're renaming them, changing 2/3 into 1/18. And if you recall, what we had to do was figure out what do we multiply a 3 by to make 18? 6. So we have to do the exact same thing to the numerator. 2 times 6 is 12. So 12/18 is equivalent to 2/3. Over here, what do we multiply the 6 by to make 24? 4. So what do we do to the 5? Times 4, which gives us 20. So 20/24 is equivalent to 5/6. Any questions there? How many of them have all 8 of them right? How many of you have all 8 correct so far? Good. So next we have the prime factoring. Prime factoring, remember, we can make the trees. What's any number that goes into 180? Well, I would use that same progression again, 10, 5, 2, 3. I can see this is divisible by 10. Now, if you picked a 2 or a 3 or a 30 or any other number that divides into 180, that would still work. So if I'm going to use 10, what's 180 divided by 10? 18. So I've broke 180 down into 10 times 18. Can 10 be broken down further? Yes, into what? 2 and 5. Now both of those are prime, so I'm going to circle them. They are done. Can 18 be broken down further? Yes, 3 times 6. 3 is prime. I'm going to circle it. That is done. 6 can be broken into 2 and 3. So that means my prime factoring of 180, I have 1, 2 2s, so 2 times 2, 1, 2 3s, so 3 times 3, and then the 5. So 180 is equal to 2 times 2 times 3 times 3 times 5. If I was asked to be put in exponential form, that would be 2 to the second power times 3 to the second power times 5. (45) x squared y, prime factor. We're going to ignore the variables. What's one number that goes into 45? 5. What would be left? 45 divided by 5 is 9. 5 is prime. 9 splits into 3 times 3. So the prime factoring of 45 is 3 times 3 times 5. How would I factor x squared? X times x, and then y. So that's it. Any questions on those? You might be left wondering, what on earth does prime factoring have to do with these fractions we were doing up here? And the answer is it has everything to do with it. I can use the prime factoring to rename fractions. Like if we have 3/5 and I'm going to convert it into 30ths. I can look at factoring those denominators. Does 5 factor? No, 5 is prime. 30, however, would factor into 2 times 3 times 5. Well, if I look at those, they both have that 5, don't they, in the denominators? But this one has stuff that the other one doesn't have, namely the 2 and the 3. So that tells me I need to multiply this one by 2 and 3, or otherwise known as 6. 2 times 3 is 6. 3 times 6 is 18. So I can use factoring to tell us what I need to do to those fractions to make them equivalent. I might have 5/12, and I want to convert it into Let's go 36. First thing I want you guys to do is I want you guys to take a minute in your notes, prime factor 12 and 36. And we'll talk about those in about 30 seconds. So 12 factors into what? Be 2 times 6, 2 is prime, 6 is 2 times 3. So 12 is 2 times 2 times 3. 36 factors into, somebody be brave. 3 and 12, you can keep going with it, right? 3 and 12, 3 is prime, 12 would be 2 and 6, 3 and 2, good. So that's 2 times 2 times 3 times 3. So we start out by looking for what they have in common. They both have a 2. They both have a second 2. They both have a 3. The difference is that 3. So what do I need to do over here? Multiply by 3 to make it 36. So 5 times 3 would be 15. So 15 over 36 is equivalent to 5 over 12. We're going to use a process similar to this for finding common denominators and changing the common denominators. So we'll see that again. The next thing we can use factoring for is reducing. When I ask you to reduce 28 over 42, we could prime factor both of those. 28 was 2 times 2 times 7. 42 is 2 times 3 times 7. Anything they have in common can be canceled out or divided out. When we reduced that, the first thing we did was divide by 2. We can cancel out the 2 that's in common. The next thing we divided by was 7. We can cancel out the 7. What's left is 2 over 3. What was the other one we had up there? I can't remember. 24 over 40. So 24 over 40, we could have done the same thing. 24, if we factor it, is 2 times 2 times 2 times 3. 40 is 2 times 2 times 2 times 5. Well, what can we cancel there? A 2. What else? Another 2 and another 2. We're left with 3 over 5. So 3/5 is how we reduce that. This, by the way, this factoring and canceling in these fractions is how we define our rules for dividing exponents. You know, we had something like x to the 5th divided by x to the 3rd. We said that was x to the 2nd. Well, it's the exact same reason. X to the 5th is 5x's multiplied together. X to the 3rd is 3x's multiplied together. You cancel out the common factors. You're left with x times x on top, which is x squared. The shortcut, of course, that we came up with was 5 minus 3 is 2. Using that now, we might be able to look at x to the 5th over x to the 8th. Using the shortcut, what does that give us for a result? X to the, 5 minus 8 is negative 3. Well, what does that mean? Well, let's do it out the long way. x to the 5th over x to the 8th. X to the 5th is 5x's. X to the 8 is 8x's multiplied together. If we cancel out 1, 2, 3, 4, 5, what are we left with? We're left with x to the 3rd on bottom. It's 1 over x to the 3rd. X to the negative 3 is equivalent to 1 over x to the 3rd. A negative exponent is a reciprocal. We'll talk about that a little bit more later on in the class. So using this now, let's actually, I want you guys to reduce one here. Let's do 12 over 60. I want you guys to reduce that. You can factor and cancel out, or you can just divide, whichever way you want to. We'll talk about it in just a second. So if we factor these, 12 factors into 2 times 2 times 3. 60 would factor into 2 times 2 times 3 times 5. Now I realize at this point it will take you guys a little bit longer to factor than I do, because you'd probably have to write out the 60 as 10 times 6, and 2 times 5, and 2 times 3. So anyway, what can we cancel? We can cancel a 2. And another 2. What else? A 3. Now everything on top canceled. What does that mean? It's a 1. If we were to try to reduce this just by dividing, you might divide the top by, well, let's say we can divide the top by 4. That gives us 3 over 15. Then we divide by 3. Well, 3 divided by 3 is 1. 15 divided by 3 is 5. If everything cancels out on either the top or the bottom of a fraction, it is a 1. Now, you guys have done a pretty good job of reducing these fractions without factoring. Why am I talking about factoring for reducing fractions? Well, we might run into something like this. 9x squared over 12x. And if I want to reduce that, we can just factor it. 9x squared, well, 9 is 3 times 3. X squared is x times x. Now I'm going to pause there. Does anybody have any questions on where the 3 times 3 times x comes from for the 9x squared? You factor the 9 into 3 times 3. And x squared is just x times x. Then we do the same for the 12x. 12 is 2 times 3. And then x is just x. What can we cancel? We can cancel a 3 and an x. Good. So what's left on top? 3 times x is 3x. And on bottom, 2 times 2 is 4. So it's 3x over 4. So let's try 15x to the third y over 21 x squared y squared. So if we factor 15 x to the third y, 15 is 3 times 5. That's as far as we can factor it. X to the third is just x, x, x. And y is just y. 21 becomes 3 times 7. X squared is x times x. Y squared is y times y. Now, as we look at this, what can we cancel out? We can cancel out a 3. Good. Anything else? We can cancel out 2 x's and a y. What's left on top? 5 times x is 5x. What's left on bottom? 7 times y is 7y. And that's it. We've reduced that fraction. I'm going to have you guys try one. Let's do 18x to the fourth y squared over let's do 30 x to the third y. I've reduced that in your notes. We'll talk about it in just a minute. So 18 factors into 233, and then 4 x's and 2 y's. 30 factors into 235, then 3 x's and a y. We cancel a 2, cancel a 3, we will cancel 3 x's and a y. On top, we have 3x and y makes 3xy. And on bottom, we just have the 5. We do have to be careful when we throw in the variables into our fractions because we can run into this situation. We'll have 24x squared y over 18 xy to the third. And when we factor those, 24 is 2 times 2 times 2 times 3. X squared becomes 2 x's, and then we have the y. 18 is 2 times 3 times 3. We have the x, and then we have 3 y's. Well, we go to cancel out here. We can cancel out a 2. We can cancel out a 3. We can cancel out an x. And we can cancel out a y. On top, we have 2 times x, which is 4x. On bottom, we have 3 times y, which is 3y squared. Now, every semester, I warn students, and every semester, a couple of you will do it anyway. We look at this, it's 4 over 3. It's really tempting to try to change that into 1 1/3, isn't it? It looks like an improper fraction, but it's not. Because there's variables in there, we cannot say for sure that this is an improper fraction because we don't know the values of x and y. They're variables, but they have a value of some sort. We just don't know what it is right now. So if x is 2 and y is 5, this is not an improper fraction. So we don't know if this is improper, therefore we won't make it that way. We must leave it like this. We will never break a fraction that has variables in it will never be broken down into a mixed number. It will always stay as it is, as just a simple fraction. Let's take a look. Let's do one more big example here. Like 35 n to the 8th d squared over 49 n to the 5th d to the 3rd. I'm going to have you try that one in your notes. We'll discuss it. So if we factor the 35 n to the 8th d squared, 35 factors into just 5 times 7. Then there are 8 n's. Should really rethink what I use for exponents here. And there are 2 d's. 49 factors into 7 times 7. There are 5 n's and 3 d's. So what can cancel? The 7 can cancel. What else? We'll get 2 d's will cancel. And 5 n's. So what we're left with on top is 5, and then n would be 5 n to the 3rd. On bottom, we have 7, and d would be 7d. Well, it is time for us to look for a shortcut. Look for a pattern so that we can use that pattern to speed up how we do things. Well, the numbers, the 35 and 49, those reduce exactly like they would even if the variables weren't there. Both of those can be divided by 7, which is why we canceled out a 7, which would give us 5 over 7. Notice that is the numerical part of our result. If we look at our variables, in the n's, we were able to cancel out 5 n's. That's because the smallest power of the n was 5. The n ended up on top in our result because the larger power in the original fraction was on top. The value here of 3, well, how would I get a 3 out of these two exponents? Subtract 8 minus 5. So let's look to see if that holds true for the d. Where is the biggest power of the d? Top or bottom? It's on bottom. In our answer, the d ends up on bottom. If I subtract the powers, I have 2 and 3. What's 3 minus 2? 1. So that's d to the 1, or just d, which is what we have. So I can use that process to make it quicker to reduce these fractions with variables in them. If I have 4, come on now, 4x to the 3rd z over 12xz squared, I can pull the numbers out and reduce them by itself. 4/12. What can I reduce that by? Both of them can divide by 2. 4 divided by 2 is 2. 12 divided by 2 is 6. Are we done? No, both of those can still be divided by another 2. 2 divided by 2 is 1. 6 divided by 2 is 3. That's as far as we can reduce it. So that tells us the numerical portion of our answer is 1 over 3. 1 in the numerator, 3 in the denominator. Now we can look at our variables. For x, is the x going to be on the top or the bottom in our result? Top, because x to the third is the largest power. Now this x on bottom really has a power of 1. So what's the power going to be on x in our result? 2. 3 minus 1 is 2. So x goes on top. 3 minus 1 is 2. Is z going to end up on top or bottom in our result? Bottom, because that's the larger power, x to the second. Again, we treat that top one as x to the 1. And what's the power of z going to be? Yeah, z to the 1 or just z, because 2 minus 1 is 1. So we can leave it as 1x squared over 3z, or we could get rid of the 1 on top, so it could just be x squared over 3z if you wanted to. Let's do another one like that. So let's do 20, a to the 5th, b to the 3rd, c to the 7th, over 15, a, b squared, oh, let's go c to the 9th. So again, we're going to start out with the numbers all by themselves. 20 times 15, what can I reduce that by? Both divide by 5. Good. 20 divided by 5 is 4. 15 divided by 5 is 3. Do I want to change that to 1 1/3? No. Because there's variables here, we're always going to leave it as improper. So it's going to be 4 in the numerator, 3 in the denominator. So we're going to look at a. We've got a to the 5th, and I'm going to make this a to the 1. Is it going to be on top or bottom? Top, because a to the 5 is the larger power. And it'll be the power of 4, because 5 minus 1 is 4. B, on top or bottom? On top, because 3 is bigger than 2, it goes on top. What's its power going to be? Just b. 3 minus 2 is 1, so it's b to the 1 or just b. C is going to go on bottom because 9 is bigger than 7. It'll be a power of, careful, 9 minus 7 is 2. You had it. It's okay. In your notes, I want you to reduce this one on your own. 42, x to the 5th, y to the 9th, over 28, x to the 9th, y to the 8th. So, I'm going to pull out the 42 over the 28. I'm going to pull out the numbers. What can both of those be divided by? What's that? Careful. 7. They can both be divided by 7. 42 divided by 7 is 6. 28 divided by 7 is 4. Are we done? No, we're not. Still divide by 2. 6 divided by 2 is 3. 4 divided by 2, 2. So in our result, we're going to have 3 in the numerator, 2 in the denominator. Where's the x go? Bottom with a power of 4. Good. Where's the y go? Top with a power of 1, or just y. So it's 3y over 2x to the 4th. How many of you had that? Okay, any questions on these? How many of you feel comfortable you could do that on a quiz? Okay, that's what I like to see. Most of the hands up. Okay, so now our next step is we want to look at the word problems that come up with this are kind of forced just because it's really hard to come up with practical word problems for stuff like this. But things like your gross pay for the year is $48,000. You pay $20,000 in taxes. What fraction of your gross pay goes to taxes? Well, here they're asking fraction of your gross pay goes to taxes. It means your taxes out of your gross pay. So the taxes are $20,000. Your gross pay is the $48,000. Now there's some divisibility rules that we didn't discuss, but hopefully you guys know. I mean, if both numbers end in 0, they can be divided by 10. If they both end in 3 zeros, they can both be divided by 1,000, right? Or we can just cross off the number of zeros that they have in common. They both have 3, so we can cross off 3 zeros, leaving us with 20 over 48. What can both of those still be reduced by? 2 or 4? 20 divided by 4 is 5, and 48 divided by 4 is 12. So the fraction of your gross pay that goes to taxes, 5/12 of your gross pay goes to taxes. A mechanical example for you, which I know is just what you wanted. 20 NF. NF stands for National Fine Thread. It's for bolts. So 20 NF means there's 20 threads per inch. So if we have a bolt, I know that looks horrible. That would be 20 threads in a 1-inch space. If I turn a nut onto that bolt, if I turn it 1 turn, it's going to advance. If I start it here and I turn that nut 1 turn, it's going to advance 1 thread. How far has it gone? Well, each thread, if there's 20 threads in an inch, each thread is 1/20th of an inch, correct? So 1 turn is 1/20th of an inch. If I turn a nut 15 turns, it's now gone onto that bolt 15/20ths of an inch. Because each turn is 1/20th, 15 turns would be 15/20ths. So to figure out how far it has advanced that nut onto the bolt, reduce that. 15 and 20 can both divide by 5 to give us 3/4 of an inch. I'm not going to talk any more about fractions like that just because it is so artificial that it's almost mind-numbing. We are about 2 minutes early for our break, but let's go ahead and take it. It's going to be 4:18 here in just a second. Okay, so we've looked at this factoring for reducing fractions like that. There are other things we can use the factoring for. We talked about greatest common factors. And that's basically what we were doing when we were reducing these fractions. Now, greatest common factor from here on out will be referred to as GCF. Factors, if you recall from last week, are numbers that will divide into that number without a remainder, without any decimal, fraction, or remainder. They divide in evenly. Greatest, of course, is assuming the largest one. Common means it has to be common to both numbers, or all three numbers if we're looking at more than two. Now, we looked at things with numbers last week, but if we throw in variables again, we might have 30 x to the fifth y squared and 20 x to the third y to the third. If we're looking for greatest common factors are basically what we are canceling out in these fractions. We factor the 30, it's 2 times 3 times 5. Of course, the x to the fifth is just 5 x's. The y squared is 2 y's. 20 is 2 times 2 times 5. X to the third is 3 x's. Y to the third is 3 y's. Now, if we were reducing a fraction here, if that were a fraction, we'd be canceling out a 2. We'd be canceling out a 5. We'd be canceling out 3 x's. And we'd be canceling out 2 y's. It's a 2, a 5, 3 x's, and 2 y's. Which multiplies back up to be 2 times 5 is 10. 3 x's makes x to the third, and the 2 y's makes y squared. That would be our greatest common factor. If that were a fraction, and I were looking to reduce it, that is what I would divide the numerator and denominator by to reduce it. Now, the way having it written out like this probably doesn't look very familiar to you. Most of the division we have done has been vertical. So it'd been the 30 x to the fifth y squared divided by 10 x to the third y squared. We would have written it like this. And we would have divided 30 divided by 10, of course, is 3. X to the fifth divided by x to the third is 5 minus 3 is 2, so x squared. And then the y squareds cancel out. So the top is going to become 3x squared. Then on the bottom, we divide the, the 20, oops, go ahead. Here, that's 30. That's a 0. Yep, then the 20, x to the third, y to the third, divided by 10, x to the third, y squared. Same type of thing. 20 divided by 10 is 2. X to the third divided by x to the third cancels out. Y to the third divided by y squared is just y. So the denominator is just 2y. So if that were a fraction, 30x to the fifth y squared over 20 x to the third y to the third, it would reduce to 3x squared over 2y. The reason being is what we crossed out when we were just canceling out factors was that greatest common factor, and it left us with 3 times x was 3x squared, and 2 times y was the 2y. So canceling out those common factors is the same as just dividing out that greatest common factor to reduce the fraction. So we can use this factoring like that to find that greatest common factor. We also used factoring to find something called a least common multiple. A least common multiple is a little bit more complex. So if I have 18 x to the third y and 12 x squared y squared, if I factor each of those, 18 is 2 times 3 times 3. Then the x to the third is just 3 x's, and then the y. 12 would factor 2 times 2 times 3. The x squared is just 2 x's, and the y squared is just 2 y's. We do look at what they have in common here. They both have a 2. They both have a 3. They both have an x and another x, and they both have a y. But then we also focus in on what they do not have in common. The top number has a 3 and a y that's not shared with the bottom number. That's telling us that they are short of common multiples by a 3 and a y. So the bottom number is going to have to be multiplied by 3 and by y to include those missing factors. Well, the bottom number has factors that the top one doesn't have. What are they? I said it's 3 and a y. That should have been 3 and an x, isn't it? That's an x that's missing, not a y. This is a 3 and an x. Sorry about that. The bottom number has numbers in it, the factors in it, that the top one is missing. It's the 2 and the extra y. So that means the top needs to be multiplied by 2y. Well, what does that give us? Well, 2 times 3 is just 18. Times another 2 is 36. X and x make x to the third. Y and another y makes y squared. So I multiplied the 18x to the third y by 2y. 18 times 2 is 36. The x to the third had no other x's to multiply, so it stayed x to the third. Y times y is y squared. On bottom, I'm multiplying by 3x, so I do the same thing. 12 times 3 is 36. X squared times x is x to the third. And then the y squared has nothing to combine with it. And I should get the same number in both spots. 36 x to the third y squared is the least common multiple of those two numbers. I'm seeing some wide eyes out there, so let's go back and do a couple with just numbers in them without the variables to remind us of the process. So let's find the least common multiple of 42 and 28. Now, one of the ways we could do this is we could just make lists. We could count up by 42. 42 plus 42 would be 84, plus another 42 would be 126, plus another 42 would be 168, and we could keep going like that. We could do the same with 28. What's 28 plus 28? 56. Plus another 28 would be 84. Well, right there, we already have a common multiple. 84 is a common multiple, and it's the smallest one. If we kept going, 28 would also be, if we kept going, we'd also be a common multiple at 168. But the 84 is smaller. Well, we want to do this with factoring. So let's go back and show that with factoring we get the same result of 84. So 42 and 28. If we factor 42, it's going to be 2 times 3 times 7. 28 factors to be 2 times 2 times 7. Now they both have a 2. They both have a 7. They also both have pieces missing. The top one has a 3, the bottom one does not. So we're going to multiply the bottom one by 3. What does the bottom one have that the top does not? A 2. So we're going to multiply the top one by 2. It's the piece that it's missing that tells us what we have to multiply it by. So 42 times 2 is 84. And 28 times 3 is 84. So there it is. 84 is the least common multiple of those numbers. Does that make more sense than just the numbers?
Break it down to the so like this would break down to 3 over 2, and then you could just flip it, right?
Oh yeah, what's left, if you cancel it out, yeah, what's left is what you'd multiply by. I see what you're saying. Yeah. Because what you're looking at is what's left over if you take out what's in common. And then you do have to exchange them. You're right. That's one way I'd never thought of before, but that's one way to think about it. Sure. And what's left over is what you multiply by, just the opposite. And that's kind of what we're doing, is the 3 and 2 are left over. The bottom one needs the 3, the top one needs the 2. What we're really doing is we're making sure that they both have all the same factors. They already both had a 2 and a 7. Well, this one had a 3, so this one needs a 3. This one had a 2, so this one needs a 2. So now they all have 2 2s, a 3, and a 7. Why is this a big deal? Well, because at some point, we're going to go to add fractions, and we're going to need a common denominator. That common denominator is the least common multiple. 6, 2 times 6. 6 factors into 2 times 3, and 8 factors into 2 times 2. Well, they both have a 2, right? This one has a 3. We need to multiply this one by 3. That's going to be 3 over 24. This one's missing. This one has the extra 2 2's, which is 2 times 2 is 4. So we're going to multiply this one by 4. That one's going to be 4 over 24. So we've created common denominators using those factors. Now, some of you might be able to look at 6 and 8 and figure out 24 as your common denominator without having to factor. But we might run into things like that. To find the common denominators there, 3 doesn't factor, but x squared is x times x. So 3x squared is 3 times x times x. 6x, well, 6 factors into 2 times 3. Then you just have the x. So again, we look at what they have in common. They both have a 3. They both have 1x. What matters is what's different. What they don't have in common. This one has an extra x, doesn't it? So this one has to be multiplied by x on top and bottom. 1 times x is x. 6x times x is 6x squared. What's extra in this one? The 2. So we have to multiply by 2 on top and bottom over here. 2 times 2 is 4. 3x squared times 2 is 6x squared. They now have common denominators. We will play with that more later. We're going to take some time to finish off our new material tonight. I want to review operations with exponents and maybe get just a little bit more complex than what we were before. Just what you kind of hear. So when I am multiplying these algebraic numbers, again, this is just 2 single-digit numbers, 1 count and the names that go along with it. We're going to multiply the counts. So here, what are the counts that we're going to multiply? 8 times 6, what do we get? 48. Then we multiply the names, and when we have more than one name, we take each name separately. So the first one would be x. We have x to the third times x to the fourth, which will be x to the seventh. Good. When we are multiplying exponents that have the same variable for the base, we add the powers. X to the third times x to the fourth. They both have a base of x, so we add the powers. 3 plus 4 is 7. How about y? That'll be y to the 7th also, because we have 5 and 2. 5 plus 2 is 7. So if I have 9x to the 5th, y is e squared, times 3 x squared y to the third. What am I going to get? Well, I combine the counts. What's that going to be? 27. 9 times 3 is 27. Then I combine the first variable in the name. Alphabetically, which one comes first? X. So let's look at the x's first. X to the 5th and x squared make x to the 7th. Good. X to the 5th times x squared. We do 5 plus 2 is 7. Alphabetically, which one comes next? Y. So we have y times y to the third makes y to the 4th. We think of that as 1. 1 plus 3 is 4. Alphabetically next is z, but we only have the z squared. Nothing to combine it with, so it's going to stay z squared. So in your notes, I want you to try to do these multiplications quick. Three x to the 7th, y to the 5th, times 5x squared z to the 3rd, and 12x to the 5th, y squared z, times 3x squared y z to the 3rd. We'll go over both of those here in just a second. So in the top one, what do you get? Perfect. That one's a little tricky because not all the variables appear in both terms. So it's 3 times 5 is 15. Alphabetically, the x comes first. So x to the 7th times x squared is x to the 9th. Alphabetically, next is the y's. That's just y to the 5th because there's nothing to combine with it. And then the z is z to the 3rd. There's nothing to combine with that. The bottom one, what do you get? 36, x to the 7th, y to the 3rd, z to the 4th. Works for me. Any questions? Okay. When we divide it then, we might have 48 x to the 5th, y to the 3rd divided by 8 x to the 3rd, y squared. We divided the counts. What's 48 divided by 8? 6. Then we divided the variables. As we saw earlier in reducing fractions, we subtract the powers. So x is going to end up being x to the 2nd. 5 minus 3 is 2. And y is going to be just y. 3 minus 2 is 1. So y to the 1 or just y. Now is where I said I was going to make it a little more complicated. We saw earlier when we had something like this. (12x to the 3rd y over 4x squared y to the 4th). If we try to divide that, 12 divided by 4 is 3. It's going to be x to the 1, or just x. 3 minus 2 is 1. Y becomes a problem, though. We've got 1 minus 4. That would be y to the negative 3. So we've got 3x, y to the negative 3. But if we go back to our reducing fractions that we saw earlier, where we factored and canceled, 12 is 2 times 2 times 3. X to the 3rd is just going to be 3 x's. And then the y. 4 is 2 times 2. X squared is going to be 2 x's. Y to the 4th is going to be 4 y's. And we cancel out the 2's. We can cancel out 2 x's. We can cancel out 1 y. We're left with 3 times x on top is 3x. On bottom, y times y times y is y to the third. That looks different than this. The answer is they are equivalent. Y to the negative 3 is the same as 1 over y to the third. So when you have a division like this where you get a negative power on one of your variables, for me, this is just fine. 3x y to the negative 3, everybody knows exactly what that means. But in my math lab, they may ask you to express your answer with positive exponents, or as positive exponents. So in order to do that, to make that y to the negative 3 a positive, we have to do its reciprocal, so it goes on the bottom of a fraction. Let me give you another example of that. Come on. So let's take 15 x to the third, y to the third, z to the third. And we're going to divide by 3, x to the fifth, y, z to the fourth. If I just divide, if it asks me to divide, I'm going to divide it out. What is 15 divided by 3? 5. X to the third divided by x to the fifth. Well, what is 3 minus 5? It's negative 2. That's x to the negative 2. How about y? Yes, this is y to the 1, so 3 minus 1 is 2, so it's y to the second. Z? Perfect. 3 minus 4 is negative 1. Now again, if this were a paper and pencil test, that answer would be fine by me. My math lab is going to most likely ask for positive exponents. So that's going to be 5. The number is going to stay. What variables have a positive power on them right now? Y. So y squared is going to stay with it. The negative powers, the x squared, or the x to the negative 2 and the z to the negative 1, are going to go on the bottom of the fraction. So x to the negative 2 is just going to be x squared on the bottom. The z to the negative 1 is going to be z to the positive 1, or just z. Any questions? Yes.
How do you determine
The one, very good. The number goes on the top. Then any of them that have positive exponents go on top. Let's do another example. 48, a to the 5, b to the second, c, over 4, a to the third, b to the third, c to the third. As you can tell, my creativity is waning for the day. So we're going to divide the numbers first. What's 48 divided by 4? 12. A to the second, 5 minus 3 is 2. B to the negative 1, 2 minus 3 is negative 1. C to the negative 2. This is c to the 1, so 1 minus 3 is negative 2. Now the question is, what stays on top? Well, basically anything that doesn't have to change stays on top. So the number doesn't have to change, and a squared is already positive, that stays on top. Everything with a negative power has to move to the bottom. So the b negative 1, that's going to go to the bottom, it's just going to be b to the 1, or b. C negative 2 moves to the denominator. We just lose the negative, it becomes c squared. What's really going on there? You're at the 12a squared. I can make that a fraction by putting it over 1. B to the negative 1, remember, is really 1 over b. It's reciprocal. C to the negative 2 is really 1 over c squared. So then when you multiply this all out, we've got 12a squared on top and b times c squared on bottom. I don't know if that makes any more sense that way or not. No? Did it? Okay. This is something we're going to come back to and loop around. We haven't seen the last of it yet. When we do an exponent of one of these algebraic numbers, so 5x to the third, y to the fifth to the sixth power, 5 to the sixth power, the 6 5's multiplied together, what does that end up being? I think it's 15,625. Somebody double check. Okay, we're good there then. So the number still has to go to the power. When we have the variables, the exponents, and we're taking that to another power, what do we do with those powers? We're going to multiply. When we multiply, we add. When we take it to the power of a power, we multiply. So that's going to be x to the 3 times 6 is 18, and y to the 30th. Very good. What if I have a fraction to a power? Well, 3/4 to the power of 3, that's implying 3/4 times 3/4 times 3/4, right? My computer's had enough for the day too, it looks like. There we go. We're just going to multiply the numerators. 3 times 3 times 3 is 3 to the third, or 27. 4 times 4 times 4 is 4 to the third, or 64. The purpose of showing this, though, is to see that when I have a fraction to a power, it really can be taken as the numerator to that power and the denominator to that power separately. So if I have 2/5 and I take each of them to the power of 5, well, I can treat that as 2 to the 5th over 5 to the 5th. 2 to the power of 5 is 32, if I can write. There it goes. It's 32. 5 to the power of 5 is 3,125. Perfect. So when we throw in three x to the 5th z over 5y squared, I can treat this as though the numerator 3x to the 5th z is to the power of 4 over the denominator 5y squared is to the power of 4. So that I can treat it as two separate problems. What's 3 to the power of 4? 81, perfect. X to the 5th to the power of 4? X to the 20th, good. When it's a variable to another power, we multiply the powers, so 5 times 4 is 20. Z, remember that's Z to the 1, so it's going to be Z to the 4th. 1 times 4 is 4. On bottom, 5 to the power of 4 is? Perfect, 625. Y squared to the 4th is Y to the 8th. Good. So we might have 10x to the 3rd y over 4 y to the 3rd z squared to the power of 3. Before I do anything with this, I should reduce the fraction that's in here. Inside those parentheses, I can reduce 10 to the 4th. What can both, or 10 over 4, what can both of those be reduced by? 2. Gives me 5 over 2. So I'm going to have 5 and 2 instead of 10 and 4. Can anything else be reduced there? Well, let's go variable by variable in alphabetical order. Which one comes first? X. Can I do anything with X? No, so the X to the 3rd just stays where it is. What's the next one? Y. Can I do anything with Y? Yes, I have Y on top and Y to the 3rd on bottom. What's that reduced to? Is it going to be on top or bottom? Bottom, because that's the bigger power. The power of 2, because we have 3 and 1. 3 minus 1 is 2. How about Z? Nothing to do there. So it just stays the Z squared on bottom. And now we still have our power of 3 out there. So we're going to split that up. So we do the numerator, 5x to the 3rd to the power of 3. And the denominator, 2y squared z squared to the power of 3. What is 5 to the 3rd power? 125. X to the 3rd power? 3 times 3 is 9, so x to the 9th. 2 to the 3rd power? 8. 8 is correct. Y squared to the 3rd power? 2 times 3 is 6. Z squared to the 3rd power? Z to the 6th. Well, I'm pretty sure I have done my share of damage for the night. So, there's a new quiz that will be due tomorrow, that's Wednesday, at 11:59 p.m. And there is a new homework that will be due on Thursday at class time. Now, just to let you off the hook a little bit so that you're not like dragging out of here with such a heavy load. The stuff in my math lab should be a little bit easier than what we covered tonight. They will eventually get up to this level of difficulty, but I wanted to kind of get you to see them now. We will see them again before we have any sort of test or anything like that on them. Okay, you guys have a good night. I'll be here till 5:20 if you have any questions. Otherwise, we'll see you on Thursday.